And this is why we would like to move on with Dr. Fischer's presentation.
Welcome, Dr. Fischer. Thank you. Dr. Markus Fischer is Divisional Director Aeronautics at the DLR. He studied aerospace engineering at the Technical University Braunschweig and did his doctorate in Hanover in the field of fluid mechanics. More than 30 years ago, he started his professional career at the DLR, so has been around for quite some time, 6 years of researching. And he worked in several companies in the field of mechanical and aerospace engineering, such as the STN Atlas Electronics, Rheinmetall Defense, and Airbus. He worked in many civil and military aircraft developments over the past decades in responsible positions in the field of research and development and engineering. And since 2017, he's back at DLR as head of Aeronautics program. And since 21, he has been divisional head in aviation. So you have a lot of experience in that field. Your presentation will consider several DLR projects where it was tested what happens if you do noise optimization and new designs in an aircraft. We've been dealing with that in the past 2 days already. And then you also look into the components that become noise optimized. And you also introduce new acoustic methods and noise measurements. Thank you very much. Dear audience, I'm really happy indeed that I can really bring it all together in this last presentation, and my dear colleagues, I look in this direction, supported me greatly. We were asked to give several presentations, and DLR does a lot in the area of the aircrafts that are in tolerance with environmental protection and how noise abatement fits into that. And I would like to try to answer that with a few slides. By the way, where is the pointer? So I will give you an insight. Into the research strategy of DLR, and a lot of things have been mentioned before. Maybe I can be briefer with some of my slides, but I would like to give you a short insight why we do what and why we have always dealt with noise. It has never ever been the situation that noise was not dealt with at the expenses of more activities in the area of CO2 reduction. That's not the case. Have we achieved enough? That's the question above. And I have selected a picture that our colleagues from the BDL have developed on the basis of the ICAO noise certification data. Lars Enholf did that. That was in the area of one of the certification points, EP-NDP, and he shows how in the past 60 years noise has drastically reduced with the increase of more modern aircrafts. And the same is also true for fuel consumption. You see that on the right-hand side top. Here you can see fuel consumption per passenger and per 100 kilometers. So you can nicely compare that with ground-based transport. And if you take a look at that today, that is the average value, 1.4 liters per passenger per 100 kilometers consumption. But that's not the end of the development. Some of the concepts that Professor Enghard introduced are also found on the right-hand side here. That is the DLR researches into most innovative configurations that at best have the two effects: flying more efficiently, less fuel consumption, and being more silent at the same time. You know that, but nevertheless, I would like to show that to you again. If we take a look at the upper curve, and these are curves that are generally accepted. These are market forecasts of Airbus, Boeing, and IATA, and others. And they all see an exponential growth for air traffic for the next decades. if we do everything that we have planned today, it will not be sufficient. Nevertheless, we have to come to this little point that says European Green Deal. So basically, the growth in front of us needs to be decoupled from CO2 emissions. So we have to clearly do more than just saying, all right, we are here now in 2023 and we only see the traffic volume of today. As a matter of fact, we forecast to the second half of this century, looking into passenger numbers and traffic volume, and then use our best possible technologies and processes and design them accordingly. It's important that we not only do the one thing and leave the other, that is CO2 or noise. No, we also want to include noise, and we would like to have an integral approach. On the left-hand side, you see a picture that I took from the ICAO. This is the noise influence area in square kilometers as a mean value across 315 airports, presented in a noise metric DNL, day-night average, DNL. And it's taken often to really determine the hearing perception of a person on the ground. And you can see how this noise, the noise carpet, so to speak, and the size of this noise carpet becomes larger and larger, and you can only counteract this when using innovative technologies. That's what is meant here, and the same is true for CO2 and non-CO2 emissions. Here, we need to improve aircraft configurations. We need to improve the processes and the operations of the future, modern engines, modern airframes, and also the use of alternative sources of energy, which includes SAF, hydrogen, and electrical energy, purely electrical energy. For that, we need to take a multidisciplinary approach. Now, we have developed a strategy going together with that in the DLR. You can download that. It says, shaping the future of aviation, and it has 4 pillars. And first of all, we deal with the energy efficient, the low emission propulsion, and we are open with respect to technologies. We look into aircraft of different sizes and then assess what the best possible use solution would be, engine configuration, propulsion concept, etc. And here we would look into different energy carriers, like hydrogen, together with fuel cells, or direct combustion of hydrogen, or sustainable fuels, bio-based fuels, or very soon synthetic fuels. And this in all different combinations of propulsions. On the right-hand side top, you see the other side of it. That's the airframe. Here we look into new configurations. We check how the energy consumption of the plane as such can be reduced drastically till 2050. We would like to reduce it by half with lightweight design, better aerodynamics, better configuration, and also the question whether we always have to fly that fast and that high as we do today, or whether we can save much more energy with this. And the first project results point to a very high potential here as well. Digitization, well, I don't want to talk about that in detail. I think that has become a backbone and allows us in this application to much earlier develop and look at radical concepts, as Professor Engelhardt showed it. With the computer system, you can really present that very quickly and easily, and in the early phase, you don't need to carry out a comprehensive experiment. And then you have the emission-reduced air transport. That is how you can operate better and thus emit less emissions, respectively having emissions that are better for the climate. As we heard from Mr. Smith before, how can I organize approach and descent differently, making sure that noise emissions can be reduced. And then I added another sentence here. As a matter of fact, low noise aviation has become an inherent objective of politics again. You have it in the coalition treaty of the present government, and we are really happy to see that. So it will be eligible for subsidies. Let me mention a few more examples. Many examples have been presented already. Let me show you how you can configure an aircraft to be more silent. This is an ongoing project of the DLR, SIAM, emission-reduced mid-range aircraft. Looks different. It's a hybrid ring body, as we call it, hybrid wing body. It's not a new configuration. We have had it since after the Second World War already, and there has been a lot of research into such a configuration. And Mr. Engelhardt said, okay, such a configuration would be appropriate, having the engines not at the underbody, but rather at the top. So to have the shielding effects and also maybe embed the engines, the propulsion, making sure that further advantages can be generated. With this configuration, they use propulsion systems that were a further development of the fan, and also in the uplift system, which has a lot of gaps and slats that also create a lot of noise. So they rather use gapless systems. They did all this and they found, great, in yellow you see the levels that could be reduced at the 3 certification points and compared to an A320 standard 2000, which is the aircraft that is mainly used nowadays. So here you would really be able to reduce a lot, reaching the goals of the ICANA Flight Path 2050. But now the but comes into play. We heard about that before. You see in this picture how such a configuration behaves compared to a standard configuration with the noise contour, the noise carpet, that is level and propagation. If you take the very precise aerodynamic methods and look at it in a multidisciplinary approach, you see that it has its price, which means, for example, that the arrangement of the engines might produce additional drag, add more weight. You have to balance that and compensate for that. You don't get it for nothing. Aerodynamics, respectively mechanics, needs to contribute as well. So what we have learned, the project is still ongoing. We have learned that right from the beginning, as it says down here, we need to have a multi-objective optimization. And here noise requirements should be an initial parameter considered right from the beginning. Now, briefly, a few words about the airframe noise research. I don't know whether the colleagues have talked about that before, but we are quite proud of the ALAN-ATRA project. In the years 2016 to 21, it was carried out with a lot of efforts. It was done together with the European project AfroNext, which we coupled and carried out simultaneously. And the objective of ALAN-ATRA was to look at a air traffic aircraft, and here all noise related measures shall be first developed and then proven in real flight operation, and then we can see how far we get with the goal that we can retrofit the existing fleet. These are measures that were flown here for future aircrafts, of course, but here the goal was first of all to do that for the existing fleet, to see what airlines could do in terms of retrofitting. And here, just a few examples, like they modified the outlet of the engine, the nozzle, and you can see the nozzle outlet, which is more hatched, and with mixing up zones of the exhaust flow, we have a lower jet noise. And there are two examples of two frequency ranges in polar radiation angle, and with such a geometrical arrangement of the nozzles, we can really reduce noise and prove it. So we proved it in the real test. Then they looked into the landing gear a lot. The landing gear is important for approach. In addition to the fuselage and airframe, it's the second largest source of noise, so it really makes sense to look into the landing gear as well. And you see that many components of the landing gear have been cladded with dampening material, with grids and what have you, and aerodynamic fairings, and that was a great success. Here you see it here in the 2 kHz frequency range. Gear down the influence of the sound pressure with an approach operation of a 320. Landing gear has been set, typical approach velocity, and you see that you could retrofit this easily, and thus the landing gear noise could be reduced. The same also for high lift. Here you see the edges of the flaps or the front part of the wings. You see these cut-off ends that also are a source of noise, and the idea was not only by molding them differently, but also by using porous materials around the edge. So it's a similar approach as Professor Engel had described for the liners. Also here, in the flight test, we saw that you can reach a lot with such methods, and on the right-hand side you can see the measurements. Here in a very broad frequency range, 2 to 3 dB reduction is possible. For the spoiler, also here we carried out some measures. You see here for the approach, if you open the spoiler, or if you open it anyways, it would open up, so you can directly look from top down, and here easily noise flow goes through, and therefore they used so-called splitter plates. So when opening the spoiler, the noise flow to the ground was prevented. That was an important factor of influence. And on the right-hand side, you see the measurement for the sound pressure across a large frequency. You could reduce a lot, but let me tell you right now, it was a big interference for the aircraft manufacturer. They said, forget about that. Finally, all the measures that were tested in flight that really offered noise reductions are presented here. There was an observer behind and in front the approaching plane and how this person perceived that. And what we consider here are the black and the white lines, curves. And you see across the Strohal number, the sound pressure level was reduced nicely, and you can claim here that the total package, Alan Atra, including other activities that be pre-tested and pre-drafted but could not be used in flight for several reasons, could offer a package of noise reduction of about 5 dB. And with a fleet, with a single A machine, you could do it. Acoustical methods and tools. I briefly want to talk about this. You see, all these things need to be measured, not only theoretically, numerically, but also in the real experiment. And for that purpose, driven by aerodynamics, we want to measure aircrafts and wind tunnels, geometrically and also in terms of flow mechanics. So they should be as close as possible to the real model. And acoustic experts have developed options here. That is part of the walls of the wind tunnels. They have the so-called arrays that work with correlation technologies, and they can measure sources of noise at the aircraft, and you can localize it highly precisely, and also the volume can be determined precisely. You see this experiment on the left-hand side in the European Transonic Wind Tunnel. That's a Embraer pattern in red. You see what they measured during the flight compared to the up and down in the wind tunnel. And you can see the sources of noise and the levels really coincide very well. So already in the wind tunnel, you can determine from the source of a noise where sound is propagated and where we have to interfere. And that goes further into the flyover experiment. Here the DLR, together with many partners, can test at airports and do the microphone arrays arranged as a spiral shape here. And with that, sources, as you see at the top, like inlet outlets of engines, can be localized precisely. Often they are the cause of tonal components. Or down here, a cavity of a drain mast that could be exactly identified, and countermeasures could be developed. I need not tell you more about this. Lars Enghert mentioned that before. There are other test rigs. The craft was mentioned before. Maybe I want to give you only a hint. There is a possibility to use inlet grids that can generate inflow disturbance patterns, and measure the influence on the fan compactor. So it's the high-resolution aerodynamic measurement and also high-resolution acoustic measurement that really determine the flow situation and disturbances, how they would impact the noise development. Last slide that I brought with me. Here I would like to advertise my dear colleagues, the expert committee aircraft noise or air traffic noise has been mentioned several times. It's a wild group, and they are not only our internal experts at DLR that advise us with all our projects, but they are also visible to the outside. They are contact partners for authorities, for committees, and what have you. And that's why I wanted to show you the names and their specialities once again. In a nutshell, last sentence, yes, the DLR has always been active in noise research, and well, we do that from the source to the recipient. With that, I would like to say thank you very much, and I'm happy to answer any questions.